Hi everyone. In this video we're going to discuss the derivatives of exponential functions, which I'm sure we're all excited to do. We're masters of trigonometric functions and inverse trigonometric functions, so this is a natural class of functions that we would like to take the derivatives of. So before we begin, we need a slightly different definition of e than we may be used to. In the context of calculus, we're going to define e as the number such that the following is true. It's going to be the number such that the limit as h goes to 0 of e to the h minus 1 all over h is equal to 1. This is our definition of e. It's the particular number such that whenever you raise it to the h minus 1 over h, you get 1. And this is kind of it seems contrived, but whenever we know what L'Hopital's rule is, we will show that this is consistent with our usual definition. We probably, hopefully, remember in pre-calculus that another way that we can define e as the asymptotic behavior of the function 1 plus 1 over x. And as x goes towards infinity, or now that we know calculus, of course, this is a limit, we approach the number e as well. Whenever we know a little bit more about derivatives, we'll be able to show that this definition is consistent with this definition. And I know what you're thinking. You're saying, well, this looks a whole lot like a derivative, doesn't it? And yeah, the answer is sure, it does. And with it, we can almost immediately say what the derivative of e to the x is. Not just a number e, but let's consider the derivative of the function e to the x. Yeah? And you say, well, I have no idea how to do this, but I know that the limit looks like it should be compatible with the limit definition of the derivative, so let's go with that. So we remember that the derivative of any function is the limit as h goes to 0, and we'll just rewrite the definition, f of x plus h minus f of x all over h. Well, let's plug in our function. This is the limit as h goes to 0. F of x plus h becomes e to the power x plus h minus e to the power x all over h. Well, let's do a little bit of algebra now. This is going to be the limit as h goes to 0. We're going to use exponent properties on this first term to write this as e to the x times e to the h minus e to the x all over h. Now let's factor out e to the x. We get e to the x, which is common in both of these terms, and what's left over? I see e to the h minus 1 all over h. And by our definition that we're going to use for e, the number e, I know that this quantity approaches 1 whenever h goes to 0, so this limit exists and it's finite. And I know that with respect to h, e to the x is just a constant, right? It's not depending upon h. So we're left with just the fun function, e to the x. And this makes us happy, right? This makes us happy. So just to state it, we have now shown that the derivative with respect to x of your favorite function, e to the x, is e to the x. Yeah? It's kind of cool. It's a function whose derivative is itself. And that's kind of interesting. All right, so let's do some examples. Let's take the derivative with respect to x of e to the power 4x plus 1. How are we going to approach this? Well, you're probably thinking, well, I should probably use the chain rule. Yeah, because I know what the derivative of e to the x is. What's the derivative of e to the stuff? Well, it's e to the stuff, right? So, what's the derivative of e to the stuff? It's e to the stuff times the derivative of what's inside. And what's the derivative of 4x plus 1? It's 4. And that's all there is to it. We're done. Let's do another example. Derivative with respect to x of 1 divided by e to the 2x. Well, you might be tempted to just go for the quotient rule, and you'd get it right. It would work. But we're mathematicians. Let's be a little lazy, right? Let's embrace the laziness. Let's rewrite this, and it's going to be a lot easier for us. Rather than division, I'm just going to make it have a negative exponent. So let's take the derivative instead of e to the power negative 2x. And what's the derivative here? Pause the video. Make sure that you're okay with this process yourself. So what's the derivative of e to the stuff? It's just e to the stuff, isn't it? And now we multiply by the derivative of what's inside. And the derivative of negative 2x is negative 2. And if you really want to, we can go back and make it look like the form that we started with by writing this as negative 2 divided by e to the power 2x. Yeah? Easy peasy. Let's do another example. Derivative with respect to x of e to the power x. Yeah? Pause the video. Try to do this yourself. All right, so what's my outermost function? First and foremost, I see the derivative with respect to x of e to the stuff, right? So what's the derivative of e to the stuff? It's e to the stuff, isn't it? Times the derivative of what's inside. And what's the function in the exponent? It's e to the x. And what's the derivative of e to the x? It's e to the x. Yeah? Cool. Let's do another one. What's the derivative with respect to x of x times e to the sine x? Pause the video. Make sure you're okay with this. So, first and foremost, I see the product of two fun functions, right? So let's use the product rule. It's the first times the derivative of the second. What's the derivative of e to the stuff? It's e to the stuff. Sorry about that. It's the first times the derivative of the second, so it's going to be the x times the derivative of e to the stuff, which is e to the stuff, times the derivative of what's inside, which is cosine of x. Plus the second, times the derivative of the first, which is just 1. And as we can see, and this will happen often whenever we have, all the time I guess, whenever we have product rule with exponential functions, I see a common factor. And so whenever we want to solve equations or solve inequalities, right, we need the number lines to solve any of our inequalities, we will want to solve it by factoring, yeah? So let's just go ahead and factor it just to make sure we're okay. I see common factors, so let's factor it out. E to the sine of x times x cosine x plus 1. And with this, we could then, set it equal to 0 and solve for x or whatever it is that we wanted to do. All right, so let's do another example. So you're bored at this point, I hope, of e to the x, and you say, boy, gee, howdy, let's take the derivative with respect to x of some function b to the power x, right? What is b here? B is just a number. B is some number, and we probably want it to be positive. Yeah, some positive number, like 2 to the x, 3 to the power x, so on. How can we take the derivative with respect to x of b to the x? Well, we're going to need some exponent properties to massage this to look like e to the stuff. And hopefully we saw this in pre-calculus, but if not, we'll walk through it step by step. This is equal to the derivative with respect to x. What's going to be really important for us in this process is remembering that x is equal to e to the natural log of x, whenever x is some positive number. Yeah? B to the x is some positive quantity, so we can write b to the x as e to the natural log of b to the power x. Okay? And that's kind of weird. It looks worse now, right? But I know that e to the natural log of any positive thing is that thing itself. So we've only done some algebra here. Now let's use exponent properties. So this is derivative with respect to x of e to the power x times the natural log of b. Now we're in business. Now we can take the derivative of e to the stuff. And remember, b is a constant, so the natural log of b is just some number. Okay? So the derivative of e to the stuff, right, is just e to the stuff times the derivative of what's inside. And what's the derivative of x times the natural log of b with respect to x? Remember, natural log of b is just a constant, so it's like 2 times x. What's the derivative of 2 times x? It's just your constant, right? So you get this funny expression. But let's rewrite it in terms of b to the x. Let's push this x back up top. And now I know that e to the natural log of anything is that thing itself. That's natural log. So we get the derivative of b to the x, where b is some positive quantity, some positive number, is b to the x times the natural log of b. Okay? What's really important here is that b needs to be a constant, not a function. It has to be a constant that's greater than 0. Constant. So let's do an example. Let's take the derivative with respect to x of 2 to the x times 5 to the power x. And I know what you're thinking. I see a product of two functions. I can do product rule. And yeah, you can, but let's not. Yeah, let's be lazy, right? We're lazy mathematicians. Let's use exponent properties. Okay? Let's use our exponent properties. What's 2 to a power times 5 to the same power? It's the derivative with respect to x of 10 to the power x, right? The bases multiply. And so now we can take the derivative with respect to x of 10 to the x, which is just 10 to the power x, times the times natural log of 10. Sorry about that. Yeah? Let's do another one. Let's take the derivative with respect to x of the secant, the inverse secant of 3 to the power x. Yeah? Pause the video and see if you can figure this out yourself. All right, so first we need to take the derivative of arc secant of stuff, right? And we know that that's going to be 1 divided by the absolute value of stuff times the square root of stuff squared minus 1. And now we need to multiply by the derivative of what's inside, right, by chain rule. Times, what's the derivative of 3 to the x? It's 3 to the power x times the natural log of 3. But we can simplify this a little bit, can't we? I know that the function 3 to the x is always positive. So what's the absolute value of something that's positive? It's the thing itself, right? So this is equal to, the absolute value of 3 to the x is just equal to 3 to the power x. And with that, I know that 3 to the x divided by 3 to the x, it's never 0. So they divide to give 1. And so really this derivative is just the natural log of 3 divided by the square root of 3 to the power 2x minus 1. Oops. All right, guys, I hope that this helps. In the next video, we will talk about derivatives of logarithms, log base e and log base b. If you have any questions about derivatives of exponential functions, feel free to reach out via email, and I can, we could set up a time to Zoom. And I look forward to seeing you in the next video. Thanks so much for watching.